Yeah. Okay, okay. Hi everybody. This is the first day of the challenge where I'll be building a CPU from scratch. I decided to take this challenge in order to work through the process of making a CPU because in this age of automation and artificial intelligence, we have forgotten the we have forgotten the enthusiasm and the fun we had while building new things. And to get an experience of that joy, I've tried to start this challenge. And yeah, I will be here building a processor from scratch every day for 2 hours and see where that gets me. Okay, then let's learn about it. And I hope to share my journey of how I am building it. I'm a final year graduate. I'm still yet to graduate. I'm pursuing my final year in BTech in Electronics and Communication Engineering. And to make things interesting, I've tried to take on this challenge. So I won't be teaching you anything. I won't be expecting you to learn from this. I'll just be sharing my journey. It'll be more like a journal and not more like a lecture. So we'll just be experiencing the process of developing something. Okay, then hope you find something meaningful in this. Okay. First, I look towards start getting a workflow for the whole process of designing the CPU. Well, am I audible? Audible? Yeah, mm, but, the phone. Wait a minute. So I'll deciding to make a RISC processor because the instruction set architecture for the RISC is open source and can be accessed by anybody. So it doesn't need me to create a new instruction set from scratch. So that part is done by people way before me. I'll just be making a model, uh, a working model of the CPU, and my time is almost okay. It's a minute right now. Okay, so I'll be learning about what workflow I need to go through to build a processor. Okay, so how to build a RISC CPU and overview. Okay, I have basic knowledge in like digital electronics and basic some surface level knowledge of computer architecture, and I learn I intend to learn them along the way to build my intuition in them and use them practically instead of just mugging up concepts. So yeah, let's see how we do this. I'm not sure. RISC-V International, I have heard of this. RISC-V International is, I think, open source organization where they build different processors, RISC-based processors. Don't worry about that. Okay. So building a RISC-V processor is the full article. And as for using AI in this challenge, I will be using AI, ChatGPT and Gemini for the challenge. But my goal is not to copy paste the code. I'll write every single line of code myself. But I will be using AI to speed up the process of learning. But I'll be writing the code by myself. Uh, It is a lot to do. Building a recipe CPU from scratch. Okay, so I'm going to or that and the workflow from it. Okay, it's an open source processor. They are like x86 and ARM are the type of architectures. Mm, so, what is the full form of this? Is reduced instruction set architecture. It's risk because it says the reduced number of instruction sets. It's type of computer processor the design that uses small simple set of instructions. Okay. So using simple set of instructions to execute the instruction, execute a program or anything. It's very quick and most of them are take only one clock cycle. Okay. What's the workflow? I don't know workflow. Uh, I found a GitHub repo describing the flow. Oh, okay. I found a GitHub repo which kind of guides me to building a RISC-V processor. Let's see if it's useful or not. Okay, that's about it. This tutorial will teach you how to build and test a fully working RISC-V symmetric core at data level and logic scale using a frequency tools to into completely private step manual as the read of the tutorial process. Setup manually. What are this one is. Hmm. This tutorial is heavily based on DDCA lectures chapter 7 on the digital design computer architecture history edition book from Sarah and David Harris. మైక్ అది కనెక్ట్ చేయాలి కదా బ్యాటరీ అయిపోతుంది 2 అవర్స్ ఉండదు బ్యాటరీ అయిపోతుంది. Uh, okay, DDCA lectures. Is this guy? I know this guy. Okay, he has a playlist of where we can learn about the RISC-V, I think. Okay, let's read about what's the what's he talking about. Okay, in the tutorial we'll be building the following core. Okay, the RISC-V core, I think. Um, from what I know, I understand some of the basic elements present here. This is an ALU, a arithmetic logic unit, which will do like addition, subtractions, and all that. The computation will happen here mostly. This is a sign extension. I don't remember what it does. I think it increases number of bits. Somehow I don't remember exactly what it is. This is a mux. Is this a mux? Oh, this is a mux. This is a program counter. It will have the address of the next instruction. This is the instruction memory from where we can extract the instructions, where we can store the instructions which will be we are planning to execute. Register file, this is like general purpose registers. I don't understand this A1, A2, A3 and all this. I don't know. ALU, I told you this is another mux. This is some control unit. Something is going on here that will make this whole thing work. Somehow it will coordinate everything together. This is a decoder. Never seen it before. data memory, I think we'll store the and load data from here. I don't know. I'm just thinking. I don't know what each things will do. I think we'll understand it as we go. On- Which aims at implementing all of the RB32 321 base instructions that you can find a table can describe the construction with implement. Um, it has instruction set. What? Why? Oh, this is the instruction set. For that. Right. Instruction set manual. Okay, so R type, I type. I don't know what this is. I don't know what's going on here. I know opcode. Opcode is the it's a unique set of bits you'll give to identify what instruction it is. Like if okay, I know what opcode is. I know LW. LW is load word. This instruction set. I think okay, yeah, I can see it's a 32 bit instruction from 0 to 31 bit. 32 bits are there here, and each range of bits is having some functionality. I think this bit will tell the opcode like which instruction is it, and all this will tell something other information. Okay, okay. I get there's so many instructions here. Oh my God, there's so many instructions. Okay, we'll come back to this later. I'm still planning the workflow. Okay, I didn't plan this at all properly. Okay, let's come back to this. Okay, we will now implement this using system verilog at register transfer level, meaning we will be focusing on the underlying logic of the CPU. Okay, we are using this head system verilog is a hardware description language. I know Verilog, I don't know system Verilog. I haven't learned it yet, and I guess I'll learn it or I'll just won't. I just will implement in Verilog instead. Maybe implement this using system Verilog at the register transfer level. So we'll be going into the registers. Okay, not at, not in the depth of gates, but we'll go to the depth of registers. We'll focus on the underlying logic of the CPU rather than low-level basics. Okay, so they won't be designing all this. Like they won't be designing full adders and bit shifts and all that. They'll look at the logic of the CPU. Okay, I don't see what that means. Disclaimer before starting: definitive source code may differ a bit as I changed simulator along the way and also fixed a few minor bugs. This should not stop you from completing it on your own way. Upward rock map, build this for the following is a book cited in the intro. Rather to have another reference on this project, which in which will select something you need to understand. So along this journey, I need to make notes. So I think I need somewhere I can start making notes about things. I guess I'll use Notion for that. Mm. So this is my Notion page. I already have some notes on Verilog. I think that's not necessary now. I will start a new notes from start a news on CPU from scratch. Okay, I'll make all my notes and things that I learn here. I'll of course make some handwritten notes, but I'll try to keep most of my learnings and targets written down in this so that they can be referenced later and I maintain a sort of pipeline flow. So first of all, there is an instruction manual. Instruction, The risk reception. Then we have what else? Then we had the BDCA lecture, BDCA lecture, and the reference book. Then next, um, for the setup manual, manual, system. Okay, so let's get back to let's get back to learning. I think I shouldn't have written plan the workflow. I can't really plan if I don't know what I'm about to do. This plan consists, okay. The plan now consists in thinking about each type of instruction we can encounter and create the logic blocks necessary to make them happen. As stated in the setup manual, bro. What is setup manual? How do I go to setup panel? Okay, the setup. Welcome back. Let's repeat how we'll use set up a project to start working as soon as possible. Uh, Prerequisites. I'll use Linux. Structure use Python programming, disk assembly, system Verilog. I don't know system Verilog. I barely know Python, and I haven't even never seen disk assembly. I don't have none of these down. Mm, Very later simulation. Okay, I don't think I need this. I have downloaded Vivado beforehand in order to. I have downloaded Vivado, as you can see. We'll be using this as I think we'll be using this as a text editor for now. Oh, this much is enough. Yeah, I think that's enough. Yeah, I have used Vivado before, but I've used it like few years back for my lab project. I think I can get this the workflow done, I guess. The workflow is basically uh, using the GitHub repo and somehow I don't know what the workflow is. Let's go to the ID environment. Mm, I don't know have any boards. I guess I'll do basis 3. have. I don't have any boards. Okay, whatever. Okay, so we are in the Vivado environment. I have used this before. I don't even inputs. Uh, I have used this before. You're using a Vivado as my code editor as well as my for the simulation and synthesis and implementation and all the steps. Um, it has a package that is everything, all the steps in one, so it'll be easier to use it. I think, yeah. Mm, okay, capture the whole screen. Mhm. Okay, I have the simulator, I have the test bench, so no need of these. Code-based structures and test setup. This course contains multiple blocks that aims at teaching different aspects of designing your own CPU. Each of these blocks has its own subfolder. Okay, subfolder like source file, test benches. Okay, FPG edition, SOC edition. Okay, test and each thing creates a bunch of log and build folders. You can get rid of them by using mm, mm. SRC will contain. SRC contains all the HTML source code. Okay, to describe all the source course logic at the RTL level. Okay, and just had the code, I guess. Test benches will have all the test benches and related hard HTML wrappers when needed. More on them. Then the next subsection packages is a folder that appears in the late single cycle edition that hosts configuration files to avoid hard coding every value. What? Okay, I don't know. I guess we'll find it out later. Um, Holy shit. Well, okay, so many modules. Okay, this is overwhelming. We have a test bench for ALU for control block for the memory. Okay, we have test benches for different modules. Test bench folder is organized like this. Make file. I don't know what to make file. Python. Right. Each module corresponds to a module present in the SRC folder. As you can see, depending on the design and the test, you can add various files needed for simulation like hex file or system file or wrapper. What are these words? Why are you so zoomed in? Browse. Hmm. So where was I? Each module corresponds to a module present in such a folder. I can see that we have the ALU file, ALU test bench here, and we have the ALU code here. As you can see, depending on the design and the test, we can add various files here to what is this? I didn't understand this. Yeah. Or I don't understand this. I just get, I will just start, I guess. Okay. Implementing the load word LW. ID, can I check the ID and one? This is the ID environment. I mean, there's nothing to talk about it. Just like simulation can be run here. I can add simulation sources here by pressing this. Click get simulation sources. I don't think we'll use it now. I think we can use it later. I just wanted to check if it's working or not. But I think this is done. Okay. Okay. I think we are on time. I think we can start learning. I think we can start learning the about risk about the word processors. Before that, I actually want to share my whole screen. Oh, hi. Yeah, I can just have it here. This is way more comfortable than window capture. Implementing the load word instruction, basic I type. So, description manual Hardly. Okay. Okay. Yeah. Hmm. Okay. Implementing the load word instruction, basic I type. I type. I type. I guess instruction. Okay. Lecture link.
Hello! In this video, we'll talk about the single cycle RISC-V processor, and in particular, implement the data path for the load word instruction. So we're going to break our processor into a data path that operates mostly on 32-bit words, the machine word size for our computer, and then a controller, break our processor, the load word instruction. So we're going to break our processor into a data path that operates mostly on 32-bit words, the machine words. So we're going to break our processor into a data path that operates mostly on
What is data path? Data path is a core group of hardware parts inside a computer central processor using the store, use and change data. Hmm? Data path is a core group of hardware parts, a group of parts inside a CPU that will store, move, and change data. The programming is executable at the computer with the consists of ROM of the processor, doing active math and logic steps. So the actual calculations, the computations are done by the data path. Means for data path, yeah, ALU data computation, adding, subtracting, logical operations. Registers don't do any computation. They just store the data, right? storage spaces that hold data the person might need. Buses are just paths for carrying data. Okay. Multiplexers also are helping choose the data path. Okay. Control unit data path moves the person's actual data. Automate acts as the boss to send signals to the path to say not operation to do something to do the hell with the data path. Mhm. Okay. Okay. Mm. Okay, so you can. I'm thinking of control unit as the one who is giving the order to execute some sort of command. It giving the commands to do some sort of action, and the actual action is being executed by the data path. The word itself, the data path, it's telling me what path the data is taking. So it's kind of the it's kind of the person who actually executes the job. I think something like that. Okay, we'll move on to the lecture. We got sidetracked.
Talk about the single cycle RISC-V processor, and in particular, implement the data path for the load word instruction. So we're going to break our processor into a data path that operates mostly on 32-bit words, the machine word size for our computer, and then a controller that receives the instruction and based on that sends back control signals to tell the data path what to do. So let's begin by designing the data path.
In the definition. Data path. Model buses, yeah, buses connection. Will data will go through process only, right? Daily will execute the data and store the data. I, I don't know.
To do. So let's begin by designing the data path. And as we're doing it, we're going to build up the capability to handle various instructions. So imagine the following program that we'll use as an example to visualize what's taking place in the data path. This program, let's say, starts at address 1. The following program that we'll use as an example to visualize what's taking place in the data path. This program, let's say, starts at address 1000 in memory, and it begins with a load word. So load x6
Okay. Okay.
from some offset relative to x9. This is an I-type instruction for load word. So this is the op for the load word.
Wait. The address where the instruction is stored. LW is shorthand notation for the load word instruction. It's an I-type instruction. What is inside or now? They said this is an offset or something.
Instruction for load word set relative to x9. This is an I-type instruction for load word. So this is the op for the load word. Its source is R9.
Opcode. Opcode. Okay, they have different opcodes because they are different instructions. This is a register, right?
Op for the load word. Its source is R9. The immediate is -4.
Media. I don't know what's going on. Okay, so I think I get what it's trying to say. Wait. This one. Okay, so it's trying to say that load instruction brings a piece of data out of the main computer memory and places it into a processor register so that processor can use it. That means it's taking the memory out of this computer memories and pressing it into this memory, I think. The processor memory where the processing can happen. Processor can use it. Fetch, after level, decode, control the data, structure, so need to go fetch and address allocation, address includes the base address and offset. That will be fine. So we are trying to load somewhere, right? We're loading it into a register. Hmm. That's what I mean. Okay, go to the memory address calculated by adding 8 to the number inside x2 register. Okay, grab the data and put it into register x5. Oh, okay, okay. Step 1, fetch the processor grabs the order card from the recipe bookmark. Decode the head shift tells it whether you will not get the to fetch from the pantry. Mm-hmm. Mm-hmm. Okay. I got it. to use yeah, beautiful tool. It has some number inside it. Okay. So when the I8 to the number inside X2 will get some address. And we need to use this address to set from the main memory a number, and that number we are going to put in okay, X5 register. This is what load word means. Loading from the memory into the register. Okay. I use it for future reference. I think this is better because mm, mm, complex instruction set architecture. In one instruction there are n micro instructions, but there are no micro instructions in RISC. It's it's just like it's looking the same. It's just there is no micro program memory, so you don't have to access the memory twice. You're just accessing the memory once, and it's much faster than CISC. And there's no more number of instructions are not there. Okay, that makes sense. There's no load word, no diagram for load word. Sign extend. Oh, sorry. Okay, we'll start from here. Okay, I'm writing what I've learned down. Rest of it is has find memory find memory load instructions. What? Oh, the five. Load instructions. Load word, load half word unsigned. What the hell? I cover load li in arithmetic. Load instructions have okay. Load word, read immediate. What the hell? Add each registration register so register RS1 holds the memory address. Even M is an address offset. Offset is a 12-bit signed immediate person is address of previous. Yeah. I can't understand it. I'll look at the video first. You will understand it later.
Word. So this is so load x6 from some offset relative.
So here we are taking the data present in X sign register, adding it -4 to it, getting an address, going to the main memory where that address is pointing to, getting the data within that memory and putting it in x6. That's I type instruction. Okay, what's an I type? I don't know. There's so many types. Okay.
To x9. This is an I-type instruction for load word. So this is the op for the load word. Its source is R9. The immediate is -4.
Nine. Oh, x9 is represented using just 9 in binary. So so registers are represented using. So I think there should be, since there are 5 bits, there should be 32 registers. And if 32 registers are there, then each register is going to be represented from 000 to 11111, right? To yeah. So we have 32 registers, and x9 means that this register. Okay, -4 is this. This is the offset, I think.
Destination
S6, 6 is this. Okay,
register. This is the op for the
I don't know what the hell it is. I don't know why it is.
load word. X6 from some offset relative to x9. This is an I-type instruction for load word. So this is the op for the load word. Its source is R9. The immediate is -4. The destination register is R.
Immediately.
The immediate is -4.
What? I thought this was 4. Oh shit, this is 2. This is 4. This is -4. Oh, -4. Is this how -4 looks like? Very good. Hmm. So it's completely different. Uh, um, How to write this following documentation? Find the positive binary 4 against the 4. Invert the bit with every 0 and 1 and 0. Add 1. Oh, okay, find the 1 supplement and add 1. Mm, okay. As you add 1, we do 1 0, 1 0. Last two bits are 0. Unsupplement representation of uh, 4 plus 4. Okay, going from here. The workflow and some project expert. Oh my god.
The destination register is R6, and F3 together with the op determined that it was a load word. And the machine language
What is this again?
the destination register is R6, and F3 together with the op determined that it was a load word. And F3 together with the op determined that it was a load word. 6, and F3 together with the op determined that it was a load word.
Oh, F3 and R. Four parts. I don't know. This is having this. Degree. Oh, yeah.
And the machine language value for this load word was FFC4A303.
How do you verify? 12, 12 bits here, 5 bits here, 2 bits here, 5 bits here, 3, 3, 10. That is 10, 20, 32 bits. So the instruction is 32 bits. And this is a hex code representation. How do the word how many bits? 2, 3, 4, 5, 6, 7, 8. So there are 8 hex, and each hex, each hex symbol is represented using 4 bits. So 8 into 4, 32. Yeah, 32 bits. So they have broken the 32 bits into uh, segments of 4 bits, and this is what they're called. It's making these 4 bits are making 3, these 4 bits are 0, these 4 bits are 3 again, these 4 bits are 8, 1 0 1 0 1 0 1 0 is 8 plus to 10. 10 is very
Next, we'll look
INTS refers to instruction.
at a store word instruction. That's an S-type instruction. And then an OR
What is
instruction.
the type, bro? ISRB. I don't know this type. What is I type? Let me clarify that. What is I type? Instruction architecture. Immediate instruction. Oh, immediate. Immediate means that I have having the contents of the okay. Oh, like this. Can't copy paste. I can't copy paste. Ah, 2048. Going till 2048. That means how many that 2048 number can be written using it's 2 to power 10 now. It's 2 to power 11. 2 to 4, yeah, 2 to power 11. That means uh, it needs 11 bits. And yeah, it needs 11 bits. 2047 needs 10 bits. Bits. Okay. Okay, immediate instruction. Immediate instructions are used for operations that involve a register and a constant value, immediate value encoded directly into the instruction itself. Okay, I-type instructions are those instructions where you'll find the instruction involve the register and immediate value, which is present in the instruction itself. Okay, and type that what is it? Uh, no, register, register, operand, operand, wherein the offering from the operating concerns in the offering and itself. It matters a little. I didn't understand why it's 204. Why can sorry that it is the whole again previous only sorry sorry wait a minute. 207 2.11 2.11 is starting 2.0. Okay, contribute 12 bits. 2.11 is the 12th bit. Correct. Okay, okay. Then that's it. Oh, mhm. 12 bits are offering 409 combinations and you are linear between positive and negative numbers. And what you're going to do is for minus and minus 2048, you have to confuse the 48 numbers and from here to 2048, which is the first step. And then how will this oh, oh, I don't know. I don't know. random representation of 12, 12 bits. Even 12 bits can cover cover our number from and 20482 two equal bits can multiply to code. You can write a code. Um,
instruction.
how did I go from there to the yeah,
Which is an R-type instruction, and then a branch on equal, a B-type instruction. And once we can run all of these, we're able to do all the interesting
I type is a very instruction and this is the immediate bit, immediate operand we have.
things in a basic program. So we're going to begin again with this load word instruction. Load word x6 from -4 parentheses x9, where x6 was the destination register, -4 was the immediate, x9 is the source register, and the op and func together make load word.
Okay.
So
I type this is the instruction, the register instruction. Okay.
make load word. So let's begin with the architectural state. Remember, we had the program counter, the instruction memory, the register file, and the data memory. And let's start by connecting the program counter to the address input of the instruction memory. So the program counter was at 1000 right here, and we'll hook that to the address of the instruction memory, and we read out from the instruction memory the machine language for the current instruction, which was FFC4A303, the load. And that's this value here on the instruction bus. Next, based on that instruction, we need to read the source registers. For load word, there's just one source register, X9. Next, based on that instruction, we need to read the source registers. For load word, there's just one source register, X9. So we take that instruction field and we'll look at the RS1 field, bits 19 through 15 of the instruction, which happen to have the value 9 because the source register was X9. We'll go into the register file, read out the value of X9, which suppose happens to be 2004.
Okay.
Happens to
What is 0x2004? What does that mean? This is 1000, and assuming it's 0 hex, that means it's 4 into 4, 16-bit address. I think so. I think 16-bit address. Oh.
Rolling out. I'm actually really tired. Um, I'm struggling to understand what it's trying to say. If 0x100 is the content of the program counter, it means the processor is currently targeting the hexadecimal memory address 0x00001000 to fetch its next instruction. It has 8, so it 432. 32.
The address bit for 32. We have 32 address bits that means after adding the hex representation, you will need 8 hex symbols. 8 symbols are using beside 8 symbols. Okay. Yeah, 8 hex symbols. Yeah. 8 number 32. Yeah, this is what I'm saying. Each symbol representing 4 binary bits. Or do you write it on slow or like okay. And what is this? So that's all.
Be 2004. Now the load word also needs an immediate offset, so we take some more bits of the instruction. Bits 31 through 20 contain the immediate for load word. And those are a bunch of ones and then 00, which in hexadecimal is FFC. Recall that we need to extend that immediate to be 32 bits long instead of 12. So we'll add a new block of immediate to be 32 bits long instead of 12. So we'll add a new block of hardware called a sign extender.
You, uh,
to extend the user
that will take in a smaller number of bits and put out a 32-bit word. Let's call that extended value IMMEXT. And so extending FFC to 32 bits is FFFFFFFC. Bunch of leading ones and then 2 zeros. So now we have the two sources for the load, 2004 and -4. The next step for load is to add the base address to the offset. So for load is to add the base address to the offset.
The next step. So first we put the program counter, got it, we got the content, we got the whole instruction. So sending it to a register file. We are trying to extract the X9 content. We got the X9 content, and we're trying to see, we're trying to extend this immediate bits. So extended immediate bits. And what we're trying to do is trying to add this content to this extended bits.
So
It's called an offset.
since we're going to be able to need to do a bunch of different kinds of arithmetic, let's put on a general arithmetic logic unit instead of just a single purpose hash. The ALU will take the two sources.
Oh, this is ALU. This is an ALU. Oh, this is just an adder, I think. Sign extender.
Source A from the register file and source B with the immediate. And it should add them. So let's provide an ALU control wire to say what the ALU should do. If we think back to chapter 5 where we defined the ALU, the code 010 meant add.
Oh, 010 means add.
So then the ALU will put out a result. Provide an ALU control wire to say and source B with the immediate. And it should add them. So let's provide an ALU control wire.
Hello. ఏమన్నా స్టిక్కింగ్ అది స్టిక్ అవ్వట్లేదు Yeah, okay. And now, 3 minutes.
To say what the ALU should do with the immediate. And it should add them. So let's provide an ALU control wire to say what the ALU should do. If we think back to chapter 5 where we defined the ALU.
Chapter 5. Chapter 5.
The code 010 meant add. So then the ALU will put out a result. That's the sum of 2004 and -4 is 2000. That's the address that we want to load from. Next, we need to read data from that address. So let's hook up ALU result to the data memory. We're putting in 2000 as the address to data memory. Data memory looks in there and it comes back with whatever value is at that address. Let's suppose the value happened to be 10. So now we'll put 10 on the data bus. And finally, we need to write that value back to the register file. So let's add a wire bringing the data out of the data memory and back to the write data terminal of the register file. The address we want to write to is register 6, which is in bits 11 through 7 of the instruction. So let's look up bits 11 through 7 of the instruction to the register file. And let's add a the address we want to write to is register 6, which was in bits 11 through 7 of the instruction. So let's hook up bits 11 through 7 of the instruction to the register.
11 to 7, okay, so bit 11 to 7, the 7 bit, so bit to vector, slice of bit.
File. And let's add a control signal called regwrite. And we'll assert regwrite so the value 10 will be written to register 6 at the end of this clock cycle.
Yeah, I mean, the data is here, and how do you know what to send it to? Write data coming in, so an address which has to connect to it. How do we do that?
And that completes what we need to do, almost completes what we need to do for load word. There's one more thing. Program counter is still at 1000. So we need to add 4 to the program counter so that we're going to the next
Oh,
instruction. So let's provide an adder. That will take the current value of the program counter and 4, add them together, we'll call that PC plus 4, and we'll bring it around as PC next, the next value of the program counter. So 1000 plus 4 makes 1004. And on the next rising edge of the clock, we'll load 1004 into the program counter, so we'll be ready to do the next instruction. And that wraps up handling load word.
Holy shit, that's a lot of time. Where is the type instruction example? Oh, okay. Load data register x6 some pointer in x9 with an offset minus 4 by address. Okay, okay, let's put it down. Okay, okay. RDF0 to I type 2 is load word. Oh, so there are several types of load words. Okay, so there are 5 types. 5 types we need for 3 bits. Okay, I don't understand this. I think I can understand this now. Load instruction has a consistent format that will illustrate with the load word. The RD is a destination register, source register RS1 holds the memory address. I understand it. It holds the memory address from where you have to extract the data which should be added to the immediate and the offset. Offset is a 12-bit signed immediate. 12-bit signed immediate, so can which if it's just 12-bit. NAT is just offset is a 12 bits and immediate, so we can reach addresses. Oh, the address in RS1. So the offset can vary from -2048 to +2047. So these are the values of offset you can take from the address which is in RS1. If you want to load the word to address 0.401. Okay, you want to load the word at address 0x140. Load immediate. Immediately load this address into the register. Doing that immediately. This is an indirectly addressing, right? Indirectly addressing or directly addressing. The address is 32 bit. The data is also 32 bits. Okay. Offset 4. 4 is an offset, which means adding 4 to yeah, because it's a 4 bytes, right? 32 bits. 12 bits. Oh my god. So much here. Look at it. Better. So we are first implementing a memory, which is oh huge.
32 bits. So that's 4 bytes long. So each word address is a multiple of 4 bytes.
What is this? I will go through this code. I have to go through this code, understand what it's doing, and I will understand what is byte address memory, memory. Okay. We'll leave blanks in the tutorial. Sometimes we will have room for creativity. Okay. Each and every time we implement something, we also test it.
verification of the memory block. When it comes to verifying memory, we simply do some writes while tinkering with the write enable flag. Now, the LLMs are bad at digital design and don't use for this code. It's critical testing, at least try to write them yourself. Late tutorial before. Here's a test bench. What is going on? I don't understand what's happening here. Like one, he wrote this in Python, which is better. Okay, this is better. So you supposed to do the Python. Speaking a lot because bit over the I think I'll use system Verilog for doing test benches because I have to learn Python for this. This memory 32-bit by 32-bit registers. Memory. Hmm. Okay. Oh, I want to open that. So I'll start writing the code for memory. I'll remove this. Okay. I need to before I need to put it on before the discussion output. Okay. This logic. Log address write data. Read data to the memory. Name read data. That's output logic also. So input logic is 32 bit. Address is 32 bit. Another input logic I want to define is write data. Um, write data. Another input logic is what? Write enable and reset. Write enable and reset. So, enable, reset then output after that. Output logic should be going from 31 down to 0. This could be my data. Good. So next we are defining the memory array and rows, algebraic rows. So first we have 32 registers, and each register and each memory register has 10 stored 0 to 64 bits. Okay. And factor is 70 factor array. Okay. So the one defined when you define the dimensions before the name, it becomes a packed array. That means you have this many set of this it's 8-bit vector basically. And if you define the dimensions after the name, it means you have individual packets, 8 individual packets of certain vectors, one bit vectors in this case. This will make it look like just makes it look like there are 256 packets of 8-bit registers. Okay. That we will be having 64 words of 32 bit. 32 bit. Right when we're going to create, we're going to have 32 bits, so it's 0 to 32, okay, 31, and then we creating memory. It's going to go from 0 to what's the word? Word minus minus 1. So now we will 31 down to 0, 31 down to 0 minus. Okay, we have created the register. Next, we will use the non-use block. Always a positive block begin Jordan and there is a particular resource is one. That means for integer the whole packet, 64 packets, what we are going to do is we are going to reset the memory to 0. Okay. And in this, I think it's not reset. If it's write enable, if write enable is 1, then the address to address bit is equal to 0, 0. That means, oh, okay. Then, okay.
Instructions. Computers use byte addressable memory, so each data byte has its own unique address.
So each data byte itself is a unique address. If you have 32 bits, that means we have a, a byte has 8 bits, right? If you have 4 bytes, it means we have 32 bits. If you have 32 bits, that means yeah, that's the whole word. So if it's being byte addressable, that means we can address each set of 8 bits individually. Okay, that means it's byte addressable. So each byte of the memory is going to have a specific address. Load store words to single byte. Load. Okay.
And we introduce load instructions that can access a byte as well as just a load instructions that and byte addressable memory. So each data byte has its own unique address. And we introduce load instructions that can access a byte as well as just a word. So a word in our processor is 32 bits. So
Yeah. The word, very good word. Okay, so like, um, memory is 32 bits long, and it's 32 bits long, and it has four bytes. Bytes of data has a unique address. Byte is basically
that's 4 bytes long. So each word address is a multiple of 4 bytes. 4 bytes long. So each word address is a multiple of 4 bytes.
each word word address is for is different by 4 bytes.
Bytes. And so
So address after we can um, so addresses we get to the next byte. Next word.
word 0 is still at address 0, but word 1 is really at address 4, not 1. Word 2 at 8, word 3 at C, word 4 at 1, 0.
Okay. So so that makes
Is a multiple of 4 bytes. And so word 0 is still at address 0, but word 1 at C, word 4 at 1, 0 next decimal. And within each of those words, there are 4 byte addresses for the bytes within the word. So if we want to read a byte addressable memory, the address of the memory word now needs to be multiplied by 4. So if we're interested in the second word, that's address 8 in memory. If we're interested in the 10th word, that's address 40 in memory, or in hexadecimal 40 is 0x28. So it's important to remember RISC-V is byte addressed, not word addressed. Let's do an example. Suppose we wanted to read the second word again. Now it's load word S3 gets 8 parentheses 0. This is the correct code on RISC-V. RISC-V is byte addressed, not word addressed. Let's do an example. Suppose we wanted to read the second word again. Now it's load word S3 gets 8 parentheses 0. This is the correct code on RISC-V. And we would read the value at
written the address directly. And the offset is initially 0. So it's offset.
word address 8 and put it into S3. Similarly, if we want to write an address, we could do a store word, T7 into address 0x10 parentheses 0. 0x10 is word hex 10, that's address hex 10, which is the fourth word in memory. And we
So this time also we're gonna try to book class. So then the four right. Then after the so we can pick the word four. That is your exception memory with the redundant classes. This is so this is 4 bytes. So this 4 bytes are coming here. Oh, okay, that's A B D C D D. Okay. So word four for address 60. Address what is address 16?
0x10 T7 into address 0x10 parentheses 0. 0x10 is word hex 10, that's address hex 10, which is the fourth word in memory. Hex 10, that's address hex 10, which is the fourth word in memory. And we would put in the value from T7. We could do
Then the little bit okay. Oh, okay. With respect to that, we go back to the code and then see when first has the reset logic. We do on this block, it happens figure x one and what try to do for as the block will begin with the block and we will everything that is the a the set of r is to the four and each one row is one then what we will do what we'll do is we'll set we run a for loop initialize I int I is equal to 0 on the initialize and we set a range of any less than 0 and then we do outlet uh, the curly bracket very long what we're going to do is we're going to move
each uh, each each packet of vegetables 0. Wow, everything is right. How big you know the that is that is. पर if also have if then नहीं होता if then नहीं होता नहीं पता if begin after that we have written for int I equal to 0 have got minus int I equal to 0 I was what different words the if it is less than word okay so sorry and I put plus and begin in primary I subtract the fine fine don't need to find the rest again maybe during assignment you cannot have the cannot have the length for the variable name as a child. What the hell? Standard of magic. Else happen. Else okay, young else condition. Again, without having yeah, you have right. Maybe. Okay, address is mm, Hyderabad address. Using the first two bits and 31 to 2
2, 1, and 0. So using the 31 to 0 is the actual address, and next to this will tell which byte it is. The word index is supposed. This is the word index. This will tell which byte of the word it is. So you can do something like x4, right? X4 is equal to 1, obviously 1, and this is 1, 0, 0, 0, 0. So this is telling me the byte. 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. So 5, 6, 7, x8. Oh, I had a fair. Okay, so what is trying to say is that the least significant two bits are used to give you the address of the byte, whereas the rest of the bits will tell you which word it is. Okay, so we are addressing the index of the word is given by the rest of the bit, and we are addressing the word and so addressing the byte using the least significant two bits. So now I'm going to bubble. What we're going to do. So, 5 very long. How to type also from system. How is this with some animal? So what are we doing? We are trying to break up the address with the right enable that means we are going to write it and put into an address. So we are inserting it along. Our data will go into the computer. So if you are going to insert other video, and then
Memory and the memory is the right data and out input to right data. That underscore data is going to the address responded by the address responded the memory address memory where the data is responded. So this is correct. So data center that data is declared separated. So I will store it in what happens so that then Always handle conversation begin where other stories read data.
Written the code for memory, but this is still remaining a doubt. Like
Plan the week and no plan for the week.
yeah, really, file extender, basic control unit.
The plan.
That's the plan for this week. I'll try to complete the implementation of load word instruction for this week. Hopefully complete the complete the whole instruction implementation and even the test even its test bench. I think it'll get done easily. I just have to learn system very long, which is another big task to do. Mm. I'll use these resources. Oh, I'll use these resources to understand more about this tree architecture. And yeah, this is what it will be. It will be me discovering the CPU workflow architecture and implementing them as we go on. So that's how the sessions will be. Mostly we focused on just learning step by step and not implementing something unless I have confidently done it myself and understood it to the full extent. So yeah, that's what I'll do every day. I'll try to keep the sessions up to 2 hours, maximum 2 hours. I'll we got extended the time way before our scheduled time, so